Okay, here's the sixth video in chapter 10. I just talked about resonance forms for depictions where the formal charge wasn't zeros across, and we were talking about the cyanide ion. This before I erase this and go on to the next example, I should point out that for each of these depictions that we had, these Lewis structure depictions, we need to do this because it is an anion, and it's not valid the way we drew it without indicating that indeed the structure represents an anion. Okay. And then of course the other thing that kind of fell out of this, I didn't really stress it up front, is that when you add up the formal charges on each of the atoms, it must add up to the charge of the ion if it is indeed an ion. And if it's not an ion, if it's a neutral molecule, then when you add up the formal charges, it must add up to zero. All right. We'll erase cyanides, and we're going to go on to another example which kind of builds on what we just talked about as well. And the molecule is going to be nitrous oxide, good old laughing gas. The formula for nitrous oxide is N2O. Okay. All right, so first step is to choose the center atom. Now, by the way, I want when I get to the end of this, I'm gonna mention something about center atoms. So actually, take it back. I'm gonna mention it right now. And so I'll just set nitrous oxide aside for just a moment, and I'm gonna draw my good old favorite molecule that I always draw, which is ethanol. And I'm gonna actually draw it out as in its Lewis structure entirely. By the way, if you remember when in the earlier videos when I was drawing ethanol, I always drew it this way. And it was the Lewis structure. So I kind of introduced you to Lewis structure really early on in this video series without really talking about Lewis structure much. But this indeed is a valid Lewis structure. In fact, you can just kind of quickly look at it and convince yourself, once you know that oxygen has two pairs here, that each of the atoms depicted here has a full octet, with the exception, of course, hydrogen, which always has its pair. Okay. Now, in the very first video in chapter 10, I mentioned that when we were talking about Lewis structure, I said you have to select a center atom. And I said, you know, sometimes you can have more than one. And in this case, if you look at this molecule, the center atom, what is the center atom? Well, is it this carbon? I guess it is, because it's sort of in the center. But you could easily make a determination that, well, this one is when trying to make a determination of how the atoms look around a center atom, we could look at this carbon and say, well, this carbon is surrounded by an H, an H, an H, and a carbon. This carbon is surrounded by an H, an H, a carbon, and an oxygen. And for that matter, even looking at the oxygen as though maybe the oxygen was the, quote, center atom, the oxygen is surrounded by a carbon and a hydrogen. So each of these atoms, all the ones other than hydrogen anyway, you can think of as being a center atom, at least with respect to thinking about its geometry. And this is what we're going to come back to when we talk about shapes. But I want to mention this now because one of the things when we talk about nitrous oxide is which is the center atom, and I wanted to kind of say, well, you know, sometimes that's a bit of a bogus kind of consideration, like in the case of ethanol. But let's go back to nitrous oxide. So least electronegative atom here is the nitrogen. And then you remember the technique is we're going to put the oxygen on one side and we're going to put the nitrogen on the other. Okay? So there's our basic building block for the Lewis structure for nitrous oxide. Well, let's count our valence electrons. Nitrogen has 5, but we got two nitrogen atoms, so it's 2 times 5. And oxygen brings 6. It's a neutral molecule, so there's no extra electrons to either add in or take out. So you add this up, and we got 16 electrons to sprinkle around. All right, let's try to figure out how we're going to do that. Well, let's see. One way is to put 2 pairs here on the center. And that's 2, 4, 6, 8. We've got 8 to go. Let's put 4 here and 4 here. All right, and let's step back and say, how did we do? Well, not great. the middle one has a full octet, the middle nitrogen that is, but the left nitrogen only has 6, so it's short, and the oxygen on the right has 6, so it's short also. All right, well, let's do our usual trick. Let's put this non-bonding pair here, and let's take this non-bonding pair and put it here. All right. Okay, let's do an octet check. The octet check shows that we have 8 around the oxygen, we have 8 around the middle nitrogen, and we have 2, 4, 6, 8 around the left. So this is what I would call a valid one. It may not be the only one, but this is certainly a valid Lewis structure. Okay. We'll come back and put formal charges on these in a second. But let me draw another one. Another one may have been like this. So instead of, let me get my cheat sheet. Yeah, instead of sprinkling the electrons like I did, let's imagine that I put 3 pairs around the oxygen. Okay, so that's 2, 4, 6, 8, 10, 12, 14, and then just 1 pair left. There, 16. Okay. All right, so that's our 16 total electrons. But again, there's an octet on the right, but there's an octet in the middle, but we're way short on the left. So let's take this pair, put it here, this pair, put it here, and let's do an octet check. Clean there, clean there, clean there. This is also another valid form. Okay, and then last, let's see. Last we could go like that, and let's put 1 here, and 1 here, and 1 there. Yep. And let's see, 2, 4, 6, 8, 10, 12, 14, 1 to go. And there. Okay. That's our first 16. Let's do an octet check. Middle's good, but both the left and the right are short. So we'll put 1 of the pairs here and 1 of the pairs here. And now do an octet check, and it looks like it's all good. So we have 3 different forms for nitrous oxide that we've come up with that are valid, at least from an octet standpoint. All right, let's calculate the formal charges, and that the formal charge calculation will give us, will allow us to judge which of these 3 are the best, and then which one's the worst. So let's do that. So the formal charge on the middle, I'm sorry, on this top variant, let's take the formal charge of the middle nitrogen. Again, nitrogen brings 5 electrons from its atom, but the way I've depicted this, there's only 1, 2, 3, 4. So it's short 1, so it has a formal charge of +1. The oxygen on the right has 6 electrons, but the way I've depicted it, it's 1, 2, 3, 4, 5, 6. So it has a formal charge of 0. Okay, it's actually not so bad. And then let's look at the left nitrogen. It has 5, but the way I've depicted it is 1, 2, 3, 4, 5, 6. 1 extra, so it has a formal charge of -1. Okay, so that's the 3 formal charges for the top variant. All right, middle variant. Formal charge in the middle nitrogen is again +1. I did that quickly because there's 5 and I only see 1, 2, 3, 4. The leftmost nitrogen brings 5 to the table, 1, 2, 3, 4, 5, so it has a formal charge of 0. And the rightmost, or the oxygen on the right, brings 6 to the table, and we have depicted as 1, 2, 3, 4, 5, 6, 7. So 1 extra electron, so it is a formal charge of -1. And then last, the variant at the bottom, again the middle nitrogen is +1. The nitrogen on the left has 5, 1, 2, 3, 4, 5, 6. I've depicted an extra electron, so it is a formal charge of -1. And the oxygen brings 6, and we have depicted as 1, 2, 3, 4, 5, 6, so it has a formal charge of 0. Okay, so for nitrous oxide, we came up with 3 different Lewis structures that are possible representations of nitrous oxide. And by calculating the formal charge in all three cases, now we can go back and say which one's most likely to be accurate, or to be a better representation of reality. All right. Well, which is the most, so first of all, from a numerical standpoint, nothing jumps out at me as being terrible. Again, terrible would be like a +2 on one side and a -2 on another, something extreme. You know, large numbers is really bad. The other thing about it is that of all three, each one has a 0, has a formal charge, has one of the atoms has a formal charge of 0, and then the other two, you know, are +1 -1 combination. So all in all, just on balance, so far everything looks like they all might be pretty good representations. But one stands out as better than the rest, and this comes back to electronegativity. The most electronegative, meaning the atom that likes electrons more than any others in this molecule, is oxygen. It's the most electronegative in the periodic table. It's to the right of nitrogen in the periodic table. So it has a more, it's more electronegative. It has a higher electron affinity. So when the formal charge on the highest electronegative atom is negative, that's a good thing. So far this strikes me as being better than the rest, because in this one, in the middle depiction, oxygen has a -1 formal charge, okay, where one of the other less electronegative atoms has a +1 charge. This one strikes me as being the best. Let's see. Oh, yeah, crikey. No wonder they look the same. The one I did at the bottom is exactly the same. Sorry, I did that wrong. I'm going to fix this really quickly. The other form is not, is actually this. I didn't draw it right. The other form is the third form. I actually reproduced the top form. Third form is this. Quickly, the formal charge on this is 0, +1, and 5b 6 7 +2. Sorry, minus 2. Oh, sorry, yeah. -2, +1, and +1. This is the third one. You can see in this particular case, this is actually one that is probably the worst. That one is the worst form because we got big numbers. We got -2, +1. We got a plus on the most electronegative. So of the three forms here that I drew, this is the worst one. Okay. This one, as we saw in comparing with the top, is the best form because it has the -1 formal charge on the most electronegative atom. And this top one is in second place in that at least the numbers look pretty good, but it has the formal charge of -1 on an atom that is less electronegative than an atom that has a formal charge of 0. So in terms of ranking these, the middle depiction is the best depiction of nitrous oxide. The top one is somewhat representative, it's certainly valid, and will contribute in a resonance kind of way as a superposition of forms. And the bottom one probably doesn't contribute much at all. Okay, that is it for resonance forms, Lewis structures, and using formal charge to make an assessment about which ones are better depictions of reality.